Students, this is the fourth video I am giving on the first unit of Topology 2. In continuation of last class, we are discussing on compact spaces. Next theorem we can discuss. Statement that X2 be a compact space and YU a Hausdorff space. F from X to Y be a one-to-one continuous function that maps X onto Y. Then F is a homeomorphism. That's what we have to prove. Anyway, we can discuss the proof. Here F is a bijection and F is a continuous function. We have to prove that F is open. That is, you take any open subset of capital X, say capital U, and prove that f of u is open. So we are taking u as an open subset X. That means x minus u is closed in X. Here capital X is compact and y is Hausdorff. So by the previous theorem, f of x minus u is closed in capital Y. That is, f of x minus f of u is closed in Y, or y minus f of u is closed in Y, or f of u is open in Y. That is, F is an open map. That is, F is a homeomorphism. That is a proof of the theorem. Next theorem, a topological space X2 is compact if and only if every family of closed subsets of X with a finite intersection property FIP has a non-empty intersection. A topological space X2 is compact if and only if every family of closed subsets of capital X with FIP has a non-empty intersection. We can discuss the proof. Suppose that X2 is a compact space. Let E alpha, collection E alpha, alpha in the index set be a family of closed subsets X with FIP. We had to prove that intersection E alpha not equal to phi. If possible, assume that intersection E alpha equal to phi, and we have to get a contradiction. Then collection X minus E alpha, alpha in index set is a collection of open sets. We consider union X minus E alpha is equal to X minus intersection E alpha is equal to X. Therefore, collection X minus E alpha, alpha in the index set is an open cover of X, and we know that X is compact, therefore the X is a finite subcovering. That is, the X is alpha 1, alpha 2, etc. alpha n in the index set such that X equal to union X minus E alpha I. That is equal to X minus intersection E alpha I. This implies intersection E alpha I equal to phi, which is a contradiction to the finite intersection property, or we are getting a contradiction, or our assumption is wrong, or intersection E alpha not equal to phi. Converse part, suppose that every family of closed subsets of X with the FIP has a non-empty intersection. That is what given, and we have to prove that X2 is compact. If possible, assume that X2 is not compact. Let theta, what is theta? The collection U alpha where alpha in index set be an open cover of X that has no finite subcovering for a capital X. You take the collection A, what is A? That is collection of X minus U alpha where alpha in index set. If possible, assume that A has no FIP. Then the X is alpha 1, alpha 2, etc. alpha n in the index set such that intersection X minus U alpha I equal to phi. That is, X minus union U alpha equal to phi, or union U alpha equal to X, which is a contradiction. Therefore, family A is a family of closed subsets of X with FIP. Therefore, by assumption, intersection X minus U alpha is not equal to phi. This implies X minus union U alpha not equal to phi. This implies union U alpha not equal to capital X. A contradiction to the fact that theta is an open cover of X. and hence we conclude that x2 is compact, or X is a compact space. Next theorem, let X2 be a topological space and let B be a basis for tau. Then X2 is compact if and only if every cover of X by members of B has a finite subcover. We are taking B as a basis here, and we are considering the collection by members of B. That is what the basis elements, that collection we are taking as an open cover. In that way the discussion is going on. Let X2 be a topological space and let B be a basis for tau. Then X2 is compact if and only if every cover of X by members of B has a finite subcover. We can discuss a proof of it. Suppose that X2 is compact. Let theta be a cover of X by members of B. Then theta is an open cover of X. Why? Because every element of B is open, because it's basis. Here X is compact and that it has a finite subcover. That is the first part. Conversely, suppose that every cover of X by members of B has a finite subcover. We have to prove that X is compact. Let theta equal to collection U alpha such that alpha in index set be an open cover of X if alpha in the index set where X is B alpha, script B alpha, subset or equal to B such that, or a collection B alpha subset or equal to B such that U alpha equal to union B, where B is the element of B alpha. Union B, U alpha is expressed as union of such B's, or B elements of B alpha. And another cover, that is theta dash, let theta dash equal to union B such that B in B alpha. Then theta dash is a cover of X by members of B. By assumption, theta dash has a finite subcover as an assumption. That is, that finite subcover we can take B1, B2, etc. Bn, that is the set B1, B2, etc. Bn, such that X equal to union Bi. I varies from 1 to n. That is X equal to B1 union B2 union etc. union Bn. For each Bi, there exists U alpha in theta such that Bi is subset or equal to U alpha I, which implies X equal to union U alpha I, or I varies from 1 to n, or X is compact. The next theorem, which is an important theorem, which is known as the tube lemma. Let X2 be a topological space and YU be a compact space. Let P in X, a point P in X, and theta be a cover of singleton set P cross Y by sets that are open in X cross Y. Then there exists a neighborhood V of P such that a finite subcollection of theta covers V cross Y. We call it as the tube lemma because see, a point P is taken and other one P cross Y. So the cross product set P cross Y, that is, you take any small y in Y, or you are getting elements in the form ordered pairs Py form, or in that way you can discuss, that is, for the fixed P there are different Y values, or you can expect that is along the Y axis, or you can discuss a tube there. That's why it is known as a tube lemma. The discussion is going on in that way. You can see the proof of it. Define H from Y to P cross Y by H of Y equal to Py, ordered pair Py. Then H is a continuous surjection. Since Y is compact and H is continuous, we have set P cross Y is compact. This implies every open cover of P cross Y has a finite subcover. So there is a finite subcollection F of theta such that F covers P cross Y. Let Y in Y, a point Y in Y. Then Py, that is an element of set P cross Y. Set P cross Y, that is equal to union Wi, because you are taking a finite union, therefore union Wi finite, where Wi is in F such that Py is in Wi. Wi is open in X cross Y, implies there is a basis element Vy cross Uy such that Py is in Vy cross Uy, which is subset or equal to Wi. Now collection Uy such that Y in Y is an open cover of Y. but y is compact. Therefore, there exists a finite subcovering. There exists y1, y2, etc. yn in y such that a capital Y equal to union uyi, where I varies from 1 to n. You take V as intersection vyi, where I varies from 1 to n. Then V is a neighborhood of P. Our claim is, or we are going to prove that V cross Y is subset or equal to union Wi. Let A be point AB in V cross Y. This implies A in V and B in Y. This implies A in V is a intersection Vyi and B is in Y. Y is a union Uyi. This implies A is an element of Vyi for all I and B is an element of Uyj for some j equal to 1 to n. This implies AB is an element of Vyi cross Uyi subset or equal to Wyi. This implies AB is an element of union Wyi, or I varies from 1 to n, which is the claim. Hence, V cross Y has a cover by a finite number of elements of theta. That is what the proof of the tube lemma. Next theorem, let x, tau and yu be compact spaces. Then x cross y is compact. That is the product space. When x and y are compact spaces, the product space x cross y is again compact. That's what we are proving. Let theta be an open cover of x cross y. Let small x in x. Then clearly theta is an open cover of set x cross y by sets open in x cross y. But y is compact. Therefore, by the previous theorem, that is the tube lemma, there exists a neighborhood Vx of x and a finite subcollection Fx of theta that covers Vx cross y. Now the collection Vx such that x in x is an open cover of x, and we know that x is compact. Therefore, there is a finite subcovering, that is, there exists x1, x2, etc. xn in x such that x equal to union Vxi, where I varies from 1 to n. Put f equal to union Fxi, where I varies from 1 to n. Then f is a finite subcollection of theta. We prove that f covers x cross y. For that, we are taking a point A, B in x cross y, which implies A in x and B in y. A in x implies A in union Vxi. This implies A in Vxi for some I. This implies AB in Vxi cross y. Since Fx is a cover of Vxi cross y, there exists W in Fxi such that AB is in W, or the point AB is in W, element of Fxi which is subset or equal to F, that is, there exists W in F such that AB in W. Hence, x cross y is compact. We can generalize the result. This is what the remark given, and the product of a finite number of compact spaces is again compact. And the result can be extended. Next theorem, let n in n and m be, capital M be a positive real number, and for each I equal to 1 to etc., let capital Xi is equal to closed interval minus m. Then the product space pi xi is compact. Proof we can discuss. We have pi xi equal to, that is, xi is minus m closed interval minus m plus m, and pi xi in the sense we are taking this n times the product of this in n times, that is pi xi, I varies from 1 to n xi is minus m cross minus m cross etc. minus m, that is minus m raised to n. We know that any closed interval in the real line is compact. Therefore, closed interval minus m is compact. Therefore, by the previous theorem, minus m raised to n is again compact, or the product space pi xi is compact. Next theorem, that is maximum minimum value theorem. Maximum minimum value theorem is important. Let x2 be a compact space and let f from x2 are a continuous function. And there exists C, D elements of x such that f of c is less than or equal to f of x, which is less than or equal to f of d for all x in x. In other words, f attains its maximum and minimum in capital X. Proof: given that x is compact and f is continuous, this implies f of x is compact. Clearly f of x is a compact subset of capital R. Then f of x is closed and bounded by the previous theorem. That means infimum fx and supremum fx both are elements of f of x. You call infimum fx as small l, supremum fx as small m, so that we can take L equal to f of c and m equal to f of d for some cd in x, or f of c is less than or equal to f of x less than or equal to f of d for all x in x. Hence the theorem follows. One question is given to conclude that part. Prove that a topological space x2 is locally connected if and only if each component of each open set is open. You can prove it. Solution: let x2 be a compact locally connected space. x2 is locally connected implies each component of each open set is open by a known theorem. In particular, each component of capital X is open. To prove that x2 has a finite number of components, for that, if possible, we assume that the number of components is infinite. Here, the collection of all components X is an open cover of X. But X is compact, implies that X is a finite subcollection of the above covering, which is impossible. Why? Because the collection of all components form a partition of X. Hence, there are only a finite number of components. That is what the solution of the problem. Or we conclude that this video here, and 9 pages and notes also you can discuss with this video. That's also attached.